Yeah, hello. Thanks for coming, everyone. Just quick show of hands. Who here has heard of A5? Okay, that's pretty good, but not everyone. So at least there was, a point to fly all the way to New Zealand. Okay, so this talk, I think some of you were in my talk yesterday, which was more talking about the kind of internals, the mathsy parts of A5, the sort of how does it work, and this one is sort of more like what it is and what it can be used for. I had two people yesterday asking, why should I use this over something else like H3? So I hope I can answer that question here as well. If at any point you want to ask a question in the middle, then raise your hand, go ahead. And I think we should have some time for questions at the end. So I'm going to start with the intro, then I'm going to do a quick demo of the website, the case study, and then talk a little bit about the ecosystem, all the places that we have A5 integrated now. Okay, so first of all, why are we even doing this? Like, what is the point of building such a system like A5 or H3, which I guess you've mostly heard of? The issue is that the world is not a flat surface. If it was, it'll be much, much, much easier to do many things in geospatial. Half of you here probably wouldn't have any jobs because it could be done by just a teenager. Things like map projections, spatial indices wouldn't be necessary. If you're going to think about dividing a flat surface like a plane, then you can divide it as in many ways, like a checkerboard or like a honeycomb. And it's pretty simple. Like even a child can kind of look at this and see that it's going to work. When you have a spherical surface, then this only works in a small patch. And if you start to extend this patch, then you are going to end up having some kind of warping in some places. Or you're going to have cells which are not going to overlap with each other. It's kind of the same problem as a map projection. So this is why people have started working with global grids, and it's definitely not something new. It's been around since maybe, I don't know, like some space missions, maybe in the 70s and 80s. In the 90s, Kevin Saar started working on hexagonal grids. There's like many, many different systems. But in data science and geospatial, at least in the kind of industry I work in, then it became really popularized by a system called H3 from Uber, which uses hexagons. And often when I talk about A5, then I compare A5 to H3, not because I'm saying H3 is the best system or something. It's just the most used one. And I think there's a few characteristics that H3 has, which people are not so aware of, and I find it useful to contrast A5 with it. Okay, so what is A5? It's a discrete global grid system, similar to H3, except rather than using hexagons, it is using irregular pentagons. There is only a single topology of each of these cells. So there's only pentagons. H3 is a bit funny in this way at first glance, that it has mostly hexagons and then 12 pentagons hidden across the sphere just because of the underlying geometry. There's no way that you can get around that. Unlike H3, A5 has equal area cells, and this is probably the biggest differentiator. The cell sizes go down to 30 square millimeters, so that's less than a square centimeter. By contrast, H3, then the cell sizes only go down to 1 meter. And another system that came even before H3 that is also kind of similar to these, called S2 by Google, goes down to 1 square centimeter. So on this level, A5 is also going to a more granular level. And all of this is indexed in a 64-bit integer because, if you want to do a sort of greater and greater granularity, you can just expand your index, and if you want to store it in 1,000 bits, then of course you can go down to like a nanometer scale, but then that wouldn't fit into a database. So I just want to give a quick example of what A5 looks like. This is just on the A5 website, which is A5Geo. My background is in visualization. My main, my real job, or at least the one that I get paid money for, is in DecGL, which is a visualization framework. And this has got a bunch of visualization layers, including H3. So I kind of came to this project from the kind of visualization side of things. So with A5, you can do similar things that you could do with H3. You can basically take a bunch of data and aggregate it into points and do this kind of like geospatial 3D bar chart. You could also just color these cells by different colors just to show some kind of density map. A useful way to compare it to H3 is this example with Airbnb data. So what this is doing is it's taking points into locations, and you can see the scale is the same. Both these circles are 10 kilometers. If you're going to use A5 to aggregate these, then the density in both places looks roughly the same. Here you have about 600, here you have almost 500. Like, you have a bit more here, but it's kind of comparable. If by contrast you use H3, then you get something slightly surprising. It looks like there's a much, much higher density here of 1,000, and here only maybe about 400. And the reason for this is that the area of a H3 cell depends on where it is on the surface of the sphere. It's not to do with the equator, it's not to do with the North Pole, it's to do with the underlying dodecahedron or icosahedron that you have there. And what does that look like? So it looks like this. So this is H3, and this is the cell sizes at a certain zoom level. It doesn't matter what zoom level you go to, the variation stays the same. It's kind of like when you have a map projection that some places are going to get warped and some places are going to end up the same size. So the smallest cell is the pentagon, but even the ones next to it are small, and the largest one is kind of in the middle of these triangles. By contrast, then A5, and this is through like a sequence of choices in the design. It's not something that's inherently to do with the pentagon. It's to do with how the pentagon helps, but it's also to do with the map projection that is used when you go from a polyhedron to the sphere. But the end result for the user is that the smallest cell and the largest cell is basically the same. I mean, this is jumping around just because there's like a rounding error between them. But you can see here on the side that as you switch between them, then it's basically the same for A5, and for H3 you have the double the size. Okay, so A5 is free to use. It's provided as an open source library. The first version that I wrote was in TypeScript. Since then, it's been ported to Python and Rust because TypeScript is not popular amongst all people. It's used for visualization, but not so much for data science. And if you want to start integrating it into maybe some kind of like database, you want some more low-level language. It's the first DGGS, as far as I know, to use a regular dodecahedron. If you want to see a bit more background on that, then maybe the talk I did yesterday was recorded, and that really goes like into the maths of why that is. It's an aperture 4 system. So this means that when you go to the next resolution level, you always get 4 times as many cells. This kind of maybe seems obvious if you think of like a chessboard being subdivided, but for example, H3 is not an aperture 4 system, it's aperture 7, because when you split a hexagon, you end up with 7 smaller hexagons. And part of what actually makes it possible to be equal area is this projection, which doesn't really have a well-established name. I think of it as something called the dodecahedral Snyder equal area projection. There is an icosahedral Snyder equal area projection, which was defined by Snyder in like 92. And that has become quite popular with icosahedral systems like H3 or, okay, no, it's not an H3, sorry. ICEA, sorry, Jerome. It's like ICEA 7H. But because no one has built a system on a dodecahedron, then normally they kind of are thinking of the icosahedron as the symmetry of this projection. But if you actually look into this paper, then both of these classes are considered. And actually, interestingly, then, even back then, Snyder said that of the globes from the 5 platonic solids, the dodecahedron, not the icosahedron, is the most distortion-free. And this is true, because this kind of spikiness of the dodecahedron is less than the icosahedron. So when you actually project from the platonic solid to the sphere, you get less angular distortion. There's some comparisons here between a bunch of different systems. These were done, I didn't do these were done independently. They're kind of comparing a bunch of systems on 2 key characteristics. So the first one is the area distortion. So you can see the A5 is just basically not distorted. All the cells are the same size. And the 2 worst systems are also the ones which are most widely in use, of course, H3 and S2. On the other side, we have something called IPQ compactness, which is some way of trying to measure like how good is the shape that we are using. And here, pretty clearly at the top, like 0.9 line, are all the hexagonal systems. So H3 does well here, but also ICF3H does well, because the hexagon is the kind of closest shape to a circle. And on that metric, then it is superior. Okay, so to answer the question that I get very, very often, hopefully, like, why does this actually matter? Like, it's all good to kind of talk about like theory. Let me just check the time. Let's compare this to like an analysis with H3. So what I'm going to do is take global Airbnb listings and try and determine which city has the kind of highest density of Airbnbs to kind of understand, well, where are the tourists going? Maybe this is interesting if you're like a travel agency or something. So what does this look like? These are just the different locations that I have my data. When I zoom into them, then I switch to this like kind of 3D bar chart, and I can do this either in A5 or in H3. So you can see that these two more or less look the same. You can see that the highest density is in the center of the city. But something interesting is happening here, and that is that as I switch between the two systems, then my top 10 changes. And some just shift up and down a bit. But for example, Buenos Aires used to be number 4, and in H3, it's just gone. Like, why is this? Why is this happening? So let's dig in a bit. If we look at the ranking using A5, then we can just count the number of listings per cell. That's on the right-hand side. And we can also normalize by the cell size. You could argue that this is the easy way that you can kind of get around the cells not being the same. With A5, the list is the same because the cells are the same area. With H3, it's a different story. If you normalize by the cell size to kind of figure out the density, you're going to get a similar ranking as you would with A5. But if you're just going to count the number of listings per cell, then you're going to get a different order. So if I combine these two into kind of one visualization, hopefully you guys can see this, then you can see that the kind of like normalized per kilometer results are quite similar. Like some of the cities get swapped around, and that's just because the sampling is not going to be quite the same. But the difference really comes here with the different cities. And you can notice that the cities which have got small cell sizes, so like this 0.07, get penalized, they get pushed down. And by contrast, the ones that have big cell sizes, so for example, Bangkok, get pushed up. And that's because like we're just, in H3, you're not actually using the same kind of catchment area to do your computation. We can actually look and plot how much these places get shifted up or down, and you can see a very kind of clear correlation here. The cities which have got the small cells get pushed down, and the ones which have the large ones get pushed up. But it's not because there's more Airbnbs there, it's just because the cells are bigger. And if you drill down into this and you look at the cities that are down here, then Buenos Aires is basically, it's kind of a bit hard to see on this, but it's basically down in the middle of this pentagon here. Or close enough. Yeah, there it is. Yeah. So all of the cities that are close to the pentagons are getting kind of penalized, and the ones which are far away are getting like an unfair boost. So in this way, and I think when you split it up into pieces like this, you can say, hey, this is obvious. But I see people doing this all of the time. They think they're doing the analysis here in the third column, but they're actually doing it here in the fourth column. They're basically forgetting that the H3 cells are not the same size. Okay, so how can you use A5? A good starting point is just to go to the website, a5geo.org. There's a bunch of visualizations that explain how it can be used, but there's also a number of quick start guides for different languages and tools. And I'm hoping over time to expand to have some kind of like recipes on how you can build these various things. A5 was only launched this year in April, I think. And I'm pretty happy with the ecosystem that has started to build up on this. So originally, I was just working on the TypeScript, and I did the port to Python and Rust. But since then, people have started to build tools on top of this. And this is actually another crucial part of what makes one of these systems useful, is having tooling in every single location. So making it possible for a user of QGIS to use this, as well as someone who's using DuckDB. And in fact, we do have these integrations. So Fang Quach, who has been sort of working with me on this a bit, he did some of the charts earlier, has got a really, really cool extension for QGIS, which is not just for A5. It does a bunch of different global grids, and it lets you do binning operations, generate grids, all of these kind of nice things without having to think about the code at all. There is now a native layer in DeckGL. Probably won't surprise you, given that I'm one of the maintainers of DeckGL, but still, it's there now, which then makes it very, very easy to visualize this. So you can just basically give DeckGL a bunch of IDs, and it's going to draw the pentagons for you, and you don't have to think about geometry, none of this stuff. A really cool one is the DuckDB integration, partly because I find DuckDB just really, really easy to use, and I think it's a great way for people to just kind of get started with geospatial. You can basically install it, and if you want to use A5, this is it. You just say, I want to load it from the community, and it does it all in the background, and then you can start doing various kind of analysis. So this actual example that I have here is on the website as well as like a recipe showing you how you can get some data from Overture Maps, bucket it into A5 cells, and then visualize it using DeckGL. And just a few days ago, at an even higher level than as part of the 30-day map challenge, there was an integration announced into Power BI. So this is like an even higher level than something like QGIS, and is making it easy for someone who's a data analyst to basically do this kind of like geospatial analysis inside Power BI, which I've never used, so I don't actually know exactly how it works, without having to sort of, install some complicated like geospatial software or anything like that. Yeah, so I think that's everything that I have. Do we have any questions?
Yes, this looks all really interesting. I've been working in DGGS a little bit off and on over the years, and I'm curious about your indexing and the aperture 4 on a pentagon. What's the relation of the parent to the child on spatial relationships, and do you use a space-filling curve still on this for the indexing?
Yeah, so there is a space-filling curve. It basically looks something like this.
Okay.
So it's like a modified Hilbert curve.
Mm-hmm.
A Hilbert curve wouldn't cross over itself, but in order to preserve at least some parent-child overlap, then I've kind of shifted it a bit. So you do have at least one level, an overlap between the parents and the children. It's definitely not as good as something like S2, which is just basically going to have, or HealPix, which has got like square cells, which are very, very simple to just cut into 4. These ones look a bit funky, but they still overlap. So you can do like some kind of level of kind of aggregation here. But this is kind of one of the sort of key metrics that you're going to want to choose between these different grid systems. Is maybe it matters to you that you need to subdivide the cells, but maybe it doesn't. Like in this analysis I was doing with Airbnb, it's like completely irrelevant.
Mm-hmm. So do the centroids of all the children lie within the parent?
No, the centroids are not there. There's just no way to do it with this pentagon, or at least I didn't come up with a way of doing it. So
cool. Thank you.
That answered my questions.
Any other questions?
I was just interested to know, was there a particular project or problem you were trying to solve with this, or is this just an idea that you had?
The latter. It's just an idea that I had. So I spent a lot of time looking at visualizations. And if I jump to the other A5 talk that I had, then I essentially came across a specific pentagonal tiling pattern, this one here on the right, in a paper from the 80s. And I've often heard this sort of argument that pentagons can't tile, and it's true. But these pentagons that you have here on the right, then they do tile to make a regular pentagon. So this was the kind of origin of this for me, that I came across this and I got kind of fascinated with the whole idea. I learned more about other systems and just wanted to see, like, is it even possible to build up something like this? And in the process, then I thought, like, okay, if I'm going to try and contribute something new, then I want it to have different characteristics to what is already available with something like H3. So that's why I really tried hard to make the cell sizes to be as small as possible, and also to go for the equal area characteristic. So trying to not just do like H3 just with pentagons, because what's the point? Yeah.
I think you just answered my question, but I'll sort of ask it anyway. Where do you see it dividing between like visualization versus analysis in terms of using the cells, you know, to do aggregations and things like that?
So I think an interesting thing about H3 or the hexagonal systems is that I've heard sometimes people using them because they just look nice, and not because they're actually good. And I've actually had the inverse, where someone complains to me they're trying to use H3 and it's really complicated because they're hexagons, and I'm like, you know, you can use a square. And they're like, no. The CEO, he likes H3, we're staying with H3. So that's kind of funny, but then on the other hand, you think like, well, if hexagons, why not pentagons? Like, if we're talking about style, then maybe you like the look of them more. There is something interesting about this tiling pattern. And by comparison, if you're using square tiles, it kind of looks like pixels. Like, I think that those are kind of ugly. As far as the kind of analysis goes, then what I was trying to do with this example here is show that, like, you don't actually even have to look at the underlying cells. Like, you can just publish the top 10, and you could use this as a way of just, you know, answering these kind of questions. So I do think that it would have value in the analysis. But honestly, like, I'm someone who comes more from visualization, and I'm trying to publicize this and get people interested and use it in their workflows and kind of tell me if it's useful. Because, like, honestly, I would be kind of making things up if I was to say, like, it's really, really good at, you know, running a big workflow on, because that's just not my background.
Was there anyone else who wanted to ask a question?
You have one? Yeah.
So H3 is not possible with equal area, right?
H3 was built with a bunch of decisions, which means that it's not equal area.
But
so
could there be a hexagon with equal area, or is that just...
Yes, if you had gone to the right talks at this conference, you would have seen. So Alex was presenting a system called IGO7. And tomorrow you should definitely go to Jerome's talk, which is going to show you a bunch of different grids. So in fact, the projection that I'm using in the system was something that Jerome introduced me to, and he's also using it in his. So as I said before, it's not a magical thing about pentagons. You can also do this with well, any shape. That's kind of the beauty of this projection.
Thank you.
Yeah, I mean, if I want to be pedantic, if I want to beat Jerome in an argument, then I often am, then I say, well, yeah, you do have equal area, but the pentagons inside the hexagonal grids are always going to be 5/6 of the hexagons. So you're always going to have, if I go back to one of these charts, where do I have this comparison? Yeah, this guy. You always kind of end up having these like little dots when you have this H in the grid, because that's kind of with the pentagons.
The latest version has less dots, so
yes, you still have a dot. You still have a dot. I said I was being pedantic. So yeah, it's true they're in the water, but like, so for me, then I'm writing the visualization code, and if you look at the layers that we have in DecGL, then the H3 hexagon one is more complicated because we have to handle the case of drawing 12 pentagons, which are not often on the screen. Whereas the other layers are much less code because you just repeat the shape. So it's true that it's an edge case, but edge cases can burn you, you know? Like, some rockets have crashed because someone had made a tiny mistake, so. Yeah.
Who was that over here who had a question? Anyone else?
Hey, I was just curious, pretty a little bit off topic, but because the Earth isn't a perfect sphere and all these are assuming it, is there much error coming from that? Or much idea around modeling like the
So
spheroid?
are you asking, does it handle the elliptic nature? Yes, it does. There's actually a nice trick that you can do here using orthalic latitude, where you basically treat the Earth as a sphere, but you slightly shift the latitude, and then everything ends up being equal area. So like if you go to this page, this V-grid, then these areas have been computed on the ellipsoid, and it's basically to the limit of the precision. Like, so within 8 decimal places, the cells in A5 and any other system that will use this projection system are going to be exactly equal area. And that I think is super nice, because then you can just forget about the size of them. And in the A5 API, there's a function which is get cell area, and all you pass it is a resolution level. Whereas in H3, you have to pass it the cell and compute it for each one and add them up. And even in the example that I had before, then I was comparing the 10 densest kilometers. Well, with A5, that's easy. You know how big a cell is, so you just kind of divide that by that. But with H3, you kind of have to, depending on the location, add up enough cells such that they make 10 kilometers. And it's just like, yeah, little things like that I think can make it a bit more, well, easy for like errors to creep into the analysis, and just add like a sort of mental load to what you're doing.
Cool. Thanks.
Thank you for coming, and thank you very much for your lecture presenting.
Yeah, thank you.